Hey, howdy everyone. So let's carry on now with this machine learning course by finally getting directly into machine learning. Everything we've covered up till now has been prerequisites for machine learning. We learned about the domain expertise behind the subsurface just a little bit, learned about coding from the perspective of building our workflows. We learned about fundamental probability and statistics. And we also covered concepts of data preparation, data bias, uncertainty in the data, and also getting into topics of feature selection and transformation. So now let's start doing some machine learning. Let's talk about the fundamental ideas behind machine learning. And so what we're going to want to do is cover the fundamental concepts and look at, for instance, the general idea or differences between inference and prediction, and training and testing, and parameters and hyperparameters, and so forth. So this will be a very general discussion. We'll use this in order to support everything else we do in machine learning from now on. Okay, so let's go ahead and get into this right now. We'll talk about, in general overview, let's start out by talking about the model. Now, up until now, we've been using these terms, but let's formalize a little bit right now. A predictor is the independent variable or feature. So what I'm saying is that variable and feature are used interchangeably. In the machine learning community, they say feature. In the geostatistical community and many other statistical communities, they use the term variable. Variable and feature, those are the different properties that we're interested in working with. Now, predictor, or the independent variable or feature, is the input into our model. It's the input variable or feature. So if we had a model, y is equal to a function of a set of variables or features x1 through xm plus some error term, then the x1 through xm are the predictor features. That's the input into our model. Now note, of course, as I said before, this term is just simply going to be some form of error. The response, or the dependent variable or feature, is the output from the model. So whereas the predictor was the x's, the response is the y's. So statistical modeling is all about estimating that function that relates predictors to response for two purposes. One is for inference, to understand the underlying system. Number two would be for the purpose of prediction, making forecasts at unsampled locations in time or space. So let's talk about each one of those. Inference. Inference is about learning about the system. If we had some type of system, f of x 1 through m, plus an error term being equal to the response, we want to understand the influence of all the x's on each other. In fact, one way to look at it is that inference is all about understanding the underlying system, not for the pure purpose of prediction, but to understand the system. And so let's think about inferential statistics. How does that work? Well, an inference problem in statistics would be, given a random sample from a population, describe the population, infer the population. Let me give you a simple example. You had 7 heads out of 10 flips. What's the probability that the coin is fair? This is exactly the example from the Bayesian tutorial by Savai, I believe in 1996 book. Now, you might think that coin flips and so forth doesn't sound very useful. Well, just change it to success wells out of 10 drilled. And now you'll see that that's a pretty powerful problem if you can infer that or learn about the underlying population and actually start to learn from that what's the true probability of a success or failure well. Prediction is about estimating that function f hat. We're representing the fact that we're estimating the function to move from x's to y's for the purpose of predicting y hat, because we're making a prediction at y. We are focused on getting the most accurate y hat, that we can get the best, most accurate y prediction. Predictive statistics are actually easier than inferential statistics. Predict the samples from a population. That's what we would do. Given 10 flips of a coin, what is the probability of 7 heads given you know the coin is fair? You know something about the underlying population. Now predict what should actually happen when we sample. Given 10 wells to be drilled, what's the probability of 7 successful wells? That's a prediction problem. Actually easier, it's more of a forward problem. Inference is more of a reverse problem, more tricky. Well, when it comes to working in machine learning, we have to make a choice of what type of methodologies to work with. There's a whole toolbox of possible methodologies that we can use. No one method performs well on all data sets. It's based on experience and understanding the data and the limitations of each one of the methods. Regardless of which method we pick, we're going to want to have a measure of the goodness of our model. One of the most common measures of goodness of the model would be a mean squared error. As we will see later on, that is an L2 norm, but for now we'll just say it's a convenient methodology by which we can measure the goodness of fit of our model. Now, if you notice, I've indexed it as I equals 1 through n, where I is equal to 1 through n training data. And we are considering 1 through m features that we're using to predict or trying to model y. And so we can do a comparison of what would we predict with our features, with our estimated function, versus what's the actual training data. 1 through n training data. Now what's very interesting is we're much more concerned about the performance of our model, the level of error of our model in the predictions we make at the locations that were not used to train the model. We denote that as locations not. These are locations that were not within the training data. We are more concerned about the performance of our model at unsampled locations, and that's why we show it as an expectation. Now we want to know how our model performs as we move away from the training data, because that's what we're going to do in practice. That's how we're going to add value with our model. So we will call this the error or the average squared error, mean squared error in testing. Now what's very interesting is that this expected or mean squared error in testing, if we take that term and we expand it, and then we expand the quadratic and we use the expectation operator, which is a nice linear operator, so we can do a lot of cool things with it, separate all the terms out, what we'll find out is that this error can be calculated as a combination, an addition of 3 error sources: model variance, model bias, and irreducible error. Now let's explain each one of them and talk about how understanding them will be critical to designing a machine learning methodology. The model variance is the variance if we had estimated the model with a different training data set, if we had changed it just a little bit. In other words, model variance is the sensitivity of the model to the actual training data that's used. Model bias is the error due to using an approximate model. The model is too simple to fit the complexity of the actual phenomenon. That's model bias. Irreducible error is a form of error that we can never escape. With the data that we have available to us, we can't get rid of irreducible error. In fact, irreducible error is due to the fact that maybe we did not sample all of the features that we need, or maybe we sampled only a limited combination or range of the features that we need to work with. And so we have not completely sampled or understood the underlying phenomenon, and so this is a reducible error. So if we were to actually look at the behavior of model variance, model bias, and irreducible error, as we change the level of complexity of the model, we go from a simple model here to a complicated model here, what we'll find is that model variance will be low for a simple model. Simple models aren't very sensitive to the data. In fact, if you change the inputs for a linear regression model, the line will change a little bit, but it's not that sensitive to the data. As we increase the complexity of the model, model variance will jump right up. If we use a 6th order polynomial, 8th order polynomial, and we change the data a little bit, the model can swing a lot more. There's a lot more sensitivity to the data that we're working with. Model bias. Well, if we use a very simple model, we have a high degree of model bias because the model is unable to handle the complexity of the natural phenomenon. You could be using a linear model to fit phenomenon that is fundamentally nonlinear. That would be high model bias. As we increase the complexity, we increase the flexibility of the model to be able to fit the data. Irreducible error, that's going to stay constant because irreducible error doesn't matter. It does not based on the model itself. It's based on the data that we have available to train the model. So using a more complicated model does not reduce irreducible error. It doesn't change it at all. So we sum them all together. They're all additive with each other. We'll get the total expected test mean squared error as this red line here, and schematically just drawn this idea of summing the three together in order to get this line right here. Now what's interesting, if we do that, what we'll find from many classes of problems that the optimum level of model complexity is not the most complicated model. It's often something that's a moderate or even sometimes a lower level of complexity has better performance, mainly because it'll have less model variance. We'll be talking about model variance, model bias, and irreducible error as we go along. So let's talk about model parameters. The best way to consider a model parameter is give ourselves a very simple example. We have one predictor feature and one response feature, and we're going to model it with a third order polynomial. Now for third order polynomial, we'll have parameters b3, the coefficient in front of the third power, b2, b1, and a constant, an intercept term. And so these are the model parameters right here. Now if we change the model parameters, we can make the model go up and down, we can change the slope, we can change the overall shape, but we still have a third order polynomial, and we can change those parameters such that we maximize our fit with the training data. In fact, that's what polygonal regression is we'll do, if we do an L2 norm, we'll minimize the squared error at all of the training data locations to get the best possible fit. Okay, so that's training the model parameters. The hyperparameters, those are different. The hyperparameters are the degree of complexity of the model. For instance, the choice of whether we use a third order, a second order, a first order, a fourth order, a fifth order, that would be a hyperparameter. Which one of those models we choose, that could be a hyperparameter that we could set. Now the problem is we can't set a hyperparameter with the training data, because if we did and we were trying to minimize the error at the training data locations, which one of these models would we pick? The linear, first order, third order, the fifth order, or the seventh order? It's pretty clear if we were trying to maximize the fit at the training data locations, we would always pick the most complicated model. It would have the greatest flexibility to be able to fit the data. But look at this model. Would this model be the best model for this data? This is clearly overfit, and we'll get into definitions and talk about overfit shortly. We'd probably do much better with a third order model in this circumstance. So what's this all tell us? We can't set the model hyperparameters from the training data. That would always make us become overfit. So we're going to take the data that's available to us and we'll divide it up into training and testing data sets. We'll extract and say if you have 100 data, maybe we'll train with 80 and we'll hold 20 to be the testing data set. And then with the training data set, we will train the model parameters to maximize the accuracy at the training data locations. And then what we could do is we can tune the model, the hyperparameters of the model, with the withheld testing data. That data is never used to set the actual parameters of each model with different complexity, but we can build models with a variety of different complexities best fit to the training data, and then we can test it against the withheld testing data, and then we can pick the model that does the best job predicting away from the training data with the best complexity to do that. So that's what tuning the hyperparameters is all about, using the withheld data that's never used to set the actual parameters of the model. Now, model complexity and flexibility. A variety of concepts may be used to describe the model complexity. In the case of in many cases, we may say the number of features that are used to build the model change the degree of complexity of the model. If we're using 1, 2, 10 features in the model, that can be used as a way to describe complexity of the model, the number of predictor features that are used, the dimensionality of the model. The number of terms and parameters. Maybe we have, as in the previous case, a linear model versus a third order model versus a fifth order or seventh order model. That would be a good way to describe the amount of complexity. There's an increasing number of parameters to train as we go to the more complicated model. And we may also consider the expression of the model. We may have a model that has a very simple, compact equation that we can use, like a polynomial type of regression model. Or we may have a situation where we have a nested set of conditional statements, like a decision tree. Or we may have a case like a neural net, where the model becomes a very complicated network of weights that average and thresholds and signals that may in fact be quite complicated and actually kind of difficult to write out. So those are different ways that we can think of complexity. In general, greater complexity leads to a higher degree of flexibility of the model, i.e., more complexity usually leads to lower model bias, but often we have greater model variance. So now we can consider once again looking at degree of flexibility or complexity. As mentioned before, it's quite common that if you increase the flexibility or complexity, you're going to decrease the mean squared error on the training data set. So this is complexity and flexibility increasing going towards the right, mean squared error shown right here. And so what happens as we increase the complexity and flexibility on training data, we're more flexible, we can fit the training data better. But what's interesting is that we may start to increase the mean squared error on testing data. In other words, we're really making worse predictions as we become more complicated. So this is not a general idea. We want to select a method that will minimize testing mean squared error and not the training mean squared error. If we do that, at this point where we are getting a more and more accurate model in training, but we're actually sacrificing the performance in testing, we are clearly becoming overfit. Let's give a very simple example to demonstrate some fundamental concepts of overfit. So let's take an example right here. It's a one-dimensional problem again. We've got the depth versus percentage of fines. So this might be like in an oil sands operation, or where we're concerned about fines inhibiting recovery from the bitumen from the sand. And so we have our data, and the data shown right here. All of our data that's available to us are training data. And now what we do is we fit a third order polynomial model. And we fit that and it performs pretty well. We calculate the distribution of the residuals. The residuals are not too big. We're doing a pretty good job. Now we set it as a fifth order polynomial. Now you notice we're starting to fit the data even more precisely. A residual distribution actually does now start to have a lower variance, lower dispersion. We're starting to do a better job fitting the training data. But look at the model confidence intervals. We can calculate the uncertainty in our model based on the amount of data we have and the variance within the data to support that model. And if we look at that, the confidence interval, I believe this is at a 95% significance level. We can see that we have pretty good confidence in the model. Relative to the shape and form of the features, we actually know something. By the time we get to fifth order, we're starting to put in a lot of wiggles and forms that are well within the confidence interval, i.e. there's not a very strong degree of certainty in that model anymore. Now look what happens when we jump up to an eighth order polynomial. We can perfectly fit the data. We're basically one order away from perfectly fitting with zero residual. We got a very tiny residual. We think we know a lot. Our R-squared model, our R-squared number is going to be very high, 0.99. We look like we know a lot, but if you calculate the confidence interval of the actual model, it's off the chart. We can't even see the upper and lower bound. In other words, none of those features have any confidence whatsoever. They're all well within a form of error. And so we have a model that's telling us we know a lot, very low residual, very high R-squared value, variance explained. But if you actually look at the model, it's actually showing us that we're fooling ourselves. We actually don't have the data to support that model. And so that is a nice illustration of overfit. So once again, what is overfit? Overly complicated model that explains the idiosyncrasies of the data, capturing data noise in the model. Model parameters, more parameters than can be justified by the data. The results in a very high error away from the data, but it's going to look like very good error at the training data, very low residual variance, very high R-squared values, very accurate at the data. You claim more than you actually know. Wikipedia had this figure right here. You have this example of a building of a segmentation decision boundary between red and blue circles. And we have one model for segmentation, which has this shape right here, the black line and the green line. The black line has some misclassification. Some red training data are on the wrong side of the decision boundary, but it kind of makes sense. The data was kind of overlapping. There seems to be some noise in this data set. Then you have the green model, which has perfect accuracy. It gets all the circles on the right side of the decision boundary, but only by doing extreme things to get that done. Clearly, we're in a case at that point where we are dramatically overfit. So, given all of that, I think we're now ready to start getting into some fundamental, some basic machine learning methodologies. And so, these methods will allow us to perform inference and prediction, to work with complicated data sets or even simple data sets, big data and small data, to detect patterns in data, to be able to find new features, to make good predictions. Remember, it's in our business to win, and usually winning is, we used to say, was having the best data. I think now it's having good data or great data and doing the best with our data. I think that's what gives us an edge. In case nobody else has done this, let me be the first to do it. Welcome to the fourth paradigm of scientific discovery, the data-driven discovery paradigm. Yeah, I say it a little bit of jesting, but all at the same time I acknowledge the fact that we are definitely in a position now where data-driven types of approaches have been quite popular and being widely used all over the place to add value. In fact, every industry in our economy is facing a digitization challenge and opportunity, as mentioned previously. Smart fields, 4D seismic, more complicated types of monitoring and sensoring, they're all leading to more and more data. We're doing a better job with data and increased computational resources. It's bringing the opportunity to use all kinds of new machine learning technologies, and there's been a lot of developments on the side of the machine learning technologies in addition to increased computational power that's really enabling us to get more done with data-driven approaches. Now we're going to start simple. We'll start with basic inferential approaches like clustering, principal component analysis, and multidimensional scaling, and then from there we're going to build up into simple to more complicated predictive methodologies. All right, I hope this basic introduction of some very, fundamental concepts of machine learning was useful to you. We covered some basic concepts around training and testing, parameters and hyperparameters, mean squared error in testing, and so forth, model variance, model bias, and irreducible error. So with that, we can get started. So I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I teach and do research in data analytics, geostatistics, and machine learning. I'm always happy to discuss. Outside the university, I guess I'm the geostats guy on Twitter and YouTube and GitHub. And so I always welcome the opportunity. I hope that the resources I share are useful to you on your journey to learn more about this topic. All right, take care.